All right. So 1702 is kind of a gifty assignment. You'll see when I start explaining it. But it's so important in biology. And if you go on in any kind of field where you're going to have to know biology. So that's why I'm making you do it regardless of how simple it's going to seem when I show it to you. Okay. So what do we know? So when we know the genotype of a parent, so that's the little r, the big R, little r, we can use that information to find out the chances that the baby's going to have a certain genotype and phenotype. So basically, if you knew that Miss Allison, who has blue eyes, so little b, has a baby with another person who has blue eyes, little b, we could predict what we're going to see. What are the odds that my baby's going to be blue-eyed? Or if I was to have a baby with a brown-eyed person, what are the odds that I might have a brown-eyed baby? Eye color, well, later on you'll learn maybe that's not the best example because eye color can be a little funny too. Okay, so, but what they're saying here is basically it doesn't really make that big of a difference to know this. If you're looking at like a cleft chin or if you're looking at earlobes or eye color, who really cares? But if you're talking about something like passing down or the likelihood of passing down something like cystic fibrosis or sickle cell anemia, or other blood-related disorders, anything that like hemophilia, anything that could potentially cause distress for the baby, then, it makes sense to kind of be looking at some of those things. So expectant parents who are planning a family, they just might want to understand the risk that they have if there is that genetic trait in their family. So what we can do is a Punnett square. So that basically is kind of the math of genetics, which I really always liked. So it gives you the chance to figure out what are the possibilities of having a child with cystic fibrosis? What are the possibilities of having a child with hemophilia? Those sorts of things. So learning task 17.2. That is, oops. Oh, sorry. Still got all my other stuff open. Nope. We'll get there. So it's this one. And what you're going to do, there's a video to watch, and you're going to write step-by-step instructions on how to make a Punnett square. That is supposed to be the only thing that you do with this, but because Punnett squares are so important if you go on at all in any kind of biology, I've kind of pulled a little bit more from the content area that I want you to do. So, which they already give the answers for it in the content area, which is where I was saying, it's kind of a silly task, but I can't not have you guys do this and feel good about it. So let's have a look. Oh, too far. Yeah. So right around this area. Okay, so obviously the videos are going to teach you a little bit about how to draw a Punnett square. Watch all those. They are super important. Don't submit to me the task until you've done these other pieces, which I know there are answers for here. However, I still want you to go through the exercise of doing it, but try to do it without looking at the answers because it is so important for you to do. So if we look at the assignment here, these are just the questions copied over from the content area. I'll just wait for that to open up. And what does it do? It says complete the Punnett square for a homozygous dominant mother. So homozygous dominant means she has big M, big M. So a homozygous dominant mother and a homozygous recessive, which means he has to have the little gene father. So when you're drawing a Punnett square, you have to put what one person has on this side and what the other person has on that side. So what are my options here? in terms of what I would get in the end with children. Mom can only give a big M. So if we go through, mom can give this big M, or oops. Oh, the internet. She can give this big M. So assuming these are the children. So child 1, 2, 3, 4 that could result. What can dad give? Dad has homozygous recessive. So a little m or a little m. So dad could give this little m when mom gives this big M, or dad could give this little m when mom gives this little m, or mom could give this big M and dad gives this little m. So you have to think about what are the possibilities, because each person can give one of their two genes. And then obviously there's the flipping of the other person's genes. So you always end up with sort of 4 possibilities. So in the end, we have a homozygous dominant mother. So we can see our baby is going to be heterozygous because the only options are big M, little m. So we know the baby's heterozygous dominant, but they're all going to have the same phenotype because we're only going to see a dominant trait. So out of all the possibilities, we're only going to get dominant responses. Let me just pull up, because I think I don't know if the learning task has you, do the probabilities. Let me just pull that up. Okay. While that loads, let's go here. Sorry for this. Hopefully you guys just skip the video ahead while I'm doing this. Oh, didn't even pull. And I think we're about halfway along. Maybe a little bit before that. Yeah, so we can have a big M, a little m, a big M, a little m, big M, a little m, blah, blah. Same thing here. So Punnett square 4, that's why you need to know what these terms mean. Heterozygous parents, where the dominant allele is unwebbed toes and the recessive is webbed toes. So if we know the parents are heterozygous, that means they're a mix. They're a big and a little. What do we also know? We know that if we looked at those parents, we would see unwebbed toes. Why? Because it's dominant. So mom can give this, dad can give this. So either mom can give her big W and dad gives his big W. And so you'd have a homozygous unwebbed toe baby. Or mom can give her little W and dad gives his big W. And you're getting a heterozygous, because you've got the mix, unwebbed toe child. If we go here, we're going to have a big W, little w. So we can have, that would be a heterozygous. And what would it be? Unwebbed, because you have one of the dominant. The only way we get the little w's is over here. Mom has to give her little w, dad has to give his little w, and you would have a little w, which would be the only child that would have recessive toe, or sorry, would have webbed toes. So if you think about that, what's the probability? So 3/4 of the time, you're going to get a baby that you're going to see that has unwebbed toes. 1/4 of the time, you're going to get a baby with webbed toes. So if we look here, these are the options. So big W, big W, big W, little w, same thing. So since unwebbed toes are dominant, the offspring must be homozygous recessive to have webbed toes. So that only happens 1 out of 4 times, which is 25% chance that you would have webbed toes, 75% chance you're not going to have webbed toes. So I like this stuff because it adds a little bit of math into science. It's kind of fun. So complete the Punnett square of a monohybrid cross where the parents have the following genotype. So what have we got? So we've got one parent that is big G, little g, and the other parent that's 2 little g's. What's the probability that any of the offspring will be homozygous recessive? So that means they have to have both little g's. So if we go here, that'd be a big G, a little g, big G, little g, 2 small g's, 2 small g's. How often is that happening out of 4? It'd be 2 out of 4, which would be what as a percentage? 50% of the time, right? So a genotype is homozygous recessive. Since 2 of the 4 are GG, then there's a 50% chance. So it's really important that you understand what homozygous recessive means, what dominant means, what heterozygous means, in order to do these kinds of problems. So this one, predict the genotype of the parents from the Punnett square above. So remember, genotype of the parent would be both of their, whether it's a big B or a little b, you need to know both. So if we look here, in order to get a B, big B and a big B and a big B and a big B, what did each of those people have to put down? It had to be a big B, right? So we could go B here, B here, B here. But then we know here we got a small b. The only place where there's a place to put the small b is here. So then you can check your answer. If you had big B, little b, you'd get that. If you had, you've got a big B there, big B, and then what would you have to have? Little b. So that makes sense. What would be the 2 genotypes? One would be big B, little b. One would be big B, big B. Okay. And then this one, you're telling me the genotype and the phenotype. Well, it's hard to tell me the phenotype when we haven't told you the trait. Let's say, yeah, anyways, we'll figure that out later. Okay, so I guess you could just tell me you'd see the dominant trait or the recessive trait, and that would be the phenotype. So again, you've got an HH, so big H with an H, little h. And then what would you get? I think, is that the final question? Yeah, that's it. So once that's all done, and I know I've given a lot of information to make that really quick, but I cannot describe how important this is if you guys continue on with biology. So I do want you to work through that. And this gets submitted to the assignment area as well.